Good morning and welcome to Saturday of week 5 of your Physics 5 a day. We've got one new nuclear video first and then nuclear practice questions. So in this video we're looking at an important graph and asking the question, why is it that some unstable nuclei decay by positron decay, some by beta decay and some by alpha decay? What sort of decides which decay mode it's going to decay by? And this graph provides the beginning of an explanation. So we've plotted the number of neutrons on this axis against the number of protons on the other axis, and then that there is the line n equals z. So anywhere along that blue line, the number of neutrons is equal to the number of protons for that nucleus. Okay, and what you find is if you're a stable nucleus, you're going to end up somewhere in this fuzzy green bit here. So if you plot your number of neutrons against your number of protons, if you're stable, you'll find that you're in here somewhere. And this is called the belt of stability. And it's a belt because it's not a clean straight line. It is actually gets wider and wider as it goes up there. Okay, but what you also notice when you plot the unstable nuclei is that those nuclei that end up in this blue bit on the graph, those are the ones that decay by beta decay. So that's emitting electrons. And on the other side, if you end up in this green section, you're most likely to decay by positron decay. And lastly, if you end up plotted to the right of this purple line here, so that means you've got more than 82 protons, then you are most likely to decay by alpha decay. Okay, but how do we understand this pattern? Well, in very simple terms, we can say that if you're in this blue section, we can see that you've got more neutrons than protons. So if this is the n equals z line, if I'm up here, I've got more neutrons than protons. And so we need to get rid of neutrons. And we know that the way that we do that is by emitting an electron. And we know from previous videos that we're emitting an antineutrino there as well, but typically that would be overlooked in one of these questions. Okay, and down here in this green section, in very simple terms, we can say if you're anywhere in there, you've got more protons than you have neutrons, and so you need to get rid of some protons, a proton. And so this is the decay you're going to do, and that's how come you're going to decay by positron decay. And then finally, if you're above 82 protons there, in very simple terms, we can say you've just got too much of both. And so to get rid of 2 of each, you do alpha decay. And the last thing to comment on is the fact that the belt of stability does not lie along the n equals z line. And importantly, it curves upwards on the n side. So if you want to be stable, if you're up here and you want to be stable, you're going to need quite a few more neutrons than protons. And we can offer an explanation for that. That's because we know that if you keep adding more and more protons, the electrostatic repulsion felt by each proton is getting bigger and bigger. This is because the electrostatic force it's not massive range, it's not like gravity, but its range is quite good. It's enough to reach from one side of a nucleus to the other. So if you're a proton on one side of a quite big nucleus, you can feel the electrostatic repulsion from all the other protons in the nucleus. But remember, you can only feel the strong force, which is the one that's going to cancel out this huge repulsion. You can only feel the strong force from your neighbours, your immediate neighbours in the nucleus. And so that is why you're going to need a lot more neutrons, which are going to exert strong forces on the protons to keep them in the nucleus. You're going to need a lot more neutrons than protons as you keep increasing the proton number. Okay, bearing all that in mind, here is the first question for today. Nice and simple. It's just so you can see a slightly different way of dealing with this material. Okay, so we can see they've done an NZ plot instead of a simple graph here, but it's the same pattern that we're looking at. There's our belt of stability up the middle. So for Z equals 7, so there's 7 protons, suggest in terms of N why an isotope may decay by beta minus. So if it's Z equals 7, it's going to be if N equals 9, 10 or 11 on this plot. And why? Because there are too many neutrons, as in there's more than the number of protons, and so you're going to need to have a neutron decay into a proton in your decay. Whereas if you're going to decay by positron decay, you are here, so that's N equals 6 or N equals 5. And then you've got too few neutrons, by which we mean N is a lot smaller than Z. And so this time you need to lose a proton. You want to try and even out your proton and neutron numbers. And that's going to involve emitting a positron. Oops, and a neutrino, not an antineutrino.